When we glide over our blue oceans and lush coastlines, it's easy to assume we won the cosmic lottery. We treat Earth as the ultimate Goldilocks zone, the absolute pinnacle of a life-sustaining planet. But these digital models represent a specific change in strategy. In October 2020, astrobiologists moved beyond the hunt for an Earth 2.0 and began identifying planets with larger surface areas and more stable climates. Scientists drew up a strict physical and chemical checklist of what a truly optimal world requires, and quickly flagged at least 24 candidates deep in space. These are classified as super-habitable planets. Because when you audit our home objectively, Earth has some severe flaws. Our sun burns fast and hot, giving complex biology a relatively narrow window to thrive, and large stretches of our own globe are completely hostile to life. If Earth isn't the peak of habitability, what exact scientific ingredients are required to build a world that outlasts and outperforms it? The first major upgrade required for a super-habitable world is sheer size. Earth, mechanically speaking, is a bit too small. When a planet has higher mass, it generates much stronger gravity. That gravity pulls down hard on the atmosphere, keeping it thick, dense, and tightly wrapped around the surface to create a highly stable climate shield. Take an exoplanet like Kepler 452b as a case study. It is roughly 60. A heavier planet provides life with an impenetrable atmospheric shield and vastly more physical real estate to experiment with than Earth ever could. The second upgrade targets the thermostat. Earth's average temperature is actually quite low for optimal biology. Our absolute highest concentrations of biodiversity are packed tightly into the warm, humid tropics. Distant star systems like TRAPPIST-1 and Gliese 667cc solve this cold problem by placing their planets in very tight, close orbits around their stars. Looking at this orbital diagram, you can see these worlds experience something called tidal locking. The planet never spins on its axis relative to its star. One half is baked in permanent daylight, and the other side is locked in an eternal, frozen night. But right there along the boundary line, where the red heat meets the deep freeze, you get the terminator zone. It is a permanent, narrow ring of twilight where liquid water flows freely and the temperature stays perpetually warm. Instead of fighting through Earth's chaotic, shifting seasons, life in this twilight strip enjoys a perfectly stable climate, giving evolution an uninterrupted, reliable runway. The third upgrade replaces the host star itself. Our sun is incredibly bright, but it burns through its fuel rapidly, giving our planet a surprisingly short biological window. It took Earth billions of years just to piece together complex organisms. By the time human intelligence arrived, we had already burned through a massive chunk of our sun's habitable timeline. Now look at this churning, dimly glowing plasma. This is a red dwarf. They burn much cooler than our sun, but they last anywhere from 20 to 70 billion years. That deep reservoir of cosmic time gives any existing biology a massive advantage. Species evolving around a red dwarf have billions of extra years to adapt, survive extinction events, and grow highly advanced. An extreme multi-billion-year runway turns out to be a far more powerful tool for cultivating complex life than starting with a perfect temperature. The final piece of a superior world requires dropping our strongest bias, the assumption that life requires Earth's exact mix of liquid water and oxygen to function. Looking at the bottom right panel of this planetary survey, we see Jupiter's moon Callisto. Both Callisto and Saturn's moon Titan harbor deep subsurface oceans and alien chemical cycles right in our own cosmic backyard. When the Cassini probe gathered data from Titan, tracked here on the monitors at the ESA control room, it detected hydrogen and acetylene mysteriously vanishing near the moon's surface. Researchers suspect those chemical compounds are being actively consumed. This points heavily toward methagenic life, organisms operating right now without a drop of liquid water, surviving entirely on liquid methane. If biology can find a way to operate in the freezing, toxic environment of our local moons, the chemical possibilities across those 24 super-habitable exoplanets are practically limitless. The ultimate recipe for life looks less like Earth and more like a massive, warm planet, locked in twilight around a long-lasting red dwarf, running on completely alien chemistry. We are actively spending billions to locate these specific conditions. You can see the Search for Earth-Sized Planets mission painted on the side of this Delta rocket, carrying the hardware needed to scan deep space. By observing how distinct species on Earth develop similar traits to solve the same environmental problems, researchers have begun to view evolution as a predictable mechanical process, one that should theoretically trigger anywhere the right physical conditions are met. Our Earth, for all its beauty, is a temporary home, with a ticking clock. But out there, hidden among thousands of other star systems, sit massive, ancient fortresses of life. Long after our sun burns out, the future survival of biology in the universe will belong to worlds that look absolutely nothing like our own.